Hey everyone. Up to this point, we've been thinking about all these ideas in physics conceptually. At this point, we're going to start moving to representing these ideas more precisely. Doing so is going to allow us to make really concrete predictions about how our systems are going to behave in the future. Now, we're not going to get to the math quite yet in this video, but we're headed in that direction. This diagram is called a temperature versus energy added diagram. It's called that because we have two things, temperature on the vertical axis and energy added on the horizontal axis. Now let's think about what these lines mean. Let's start with this slanted diagonal line here. What does it mean when we're going up and to the right? Well, because energy is on the horizontal axis and temperature is on the vertical axis, going up and to the right means energy is increasing and temperature is increasing. As we discussed, adding energy into the thermal energy of a substance causes it to warm up. If we remove energy, it causes it to cool down. That's just represented by going the opposite direction on this diagram, from top right to bottom left. But what about these horizontal lines? Well, what does a horizontal line represent on this graph? A horizontal line is just a spot where energy is being added to the system, but the temperature is not changing. What could that be? Well, it's just the phase change. In this class, we are going to separate changes in thermal energy and changes in bond energy, changes in temperature and changes in phase. In our model, a substance must completely change its phase before its temperature can change. In other words, if a substance temperature is changing, then its phase is not changing. And if a substance phase is changing, then its temperature is not changing. Let's say that this diagram represents the temperature versus energy added for water. Down here at the bottom left, we have ice. The ice slowly warms up, and then its phase changes. It starts to melt. Once it's fully melted, it begins to warm up again, this time as water. Eventually, it reaches its boiling point. At its boiling point, it now turns into steam. It changes phase. Once it becomes steam, it is now again allowed to warm up. Now, this might be useful, but it's not super precise, and it's not clear how we would use it if we were trying to understand the situation with both ice and coffee. So let's move on to the energy interaction diagram. The energy interaction diagram is just a graphical way of representing the exchange in energy that happens when you put two objects in contact with each other. Let's try to build an energy interaction diagram for the case of the coffee and the ice cube. First, let's think about what kinds of energy are going to be changing. Let's start with the coffee, since that's the easiest. We know that when it's all said and done, the coffee will have cooled down from its original temperature because of the ice cube. All that's happening is the thermal energy of the coffee is going down as its temperature decreases. That's fairly simple. But now let's think about it from the perspective of the ice cube. Let's say that the ice cube's original temperature is its melting temperature, 0 degrees Celsius. When we put it into the mug, it's immediately going to start melting. Its bond energy is going to change as it goes from solid to liquid. Well, remember, in our models, the temperature of a substance is not allowed to change until its phase has completely changed. So once the ice cube is melted, we now have a bunch of water at 0 degrees Celsius. This water is surrounded by hot coffee. So what's going to happen now? It's going to try to warm up to the temperature of the coffee. Its thermal energy is going to increase. Let's see how we can represent that with an energy interaction diagram. Energy interaction diagrams are also called bubble diagrams because we draw bubbles for every energy system. In this case, we have three energy systems: the bond energy of the ice, the thermal energy of the ice after it melts, and the thermal energy of the coffee. So we need three bubbles. The the first thing that we actually add to an energy interaction diagram is not any information in these bubbles. We start by saying very explicitly what our physical system is. What are the things in the problem that we care about? In this case, it's just two things, the ice cube and the coffee. While the ice cube and the coffee are in this mug, the mug is not actually part of the problem. It's just the container that this stuff is happening in. Now we're going to start to fill in these bubbles with actual information. Remember, these bubbles represent the kinds of energy that are present in the system. There's three: the thermal energy of the coffee, the bond energy of the ice cube, and then the thermal energy of the melted water as it warms up. We start by labeling these energy bubbles according to which substance they correspond to. Two of the energy bubbles correspond to the ice and the water that it turns into. The third bubble corresponds to the thermal energy of the coffee. Let's start by filling in this leftmost bubble, the ice bubble. The next thing we want to do is think about what kind of energy this bubble represents. In this case, we're going to use this bubble to represent the bond energy of the ice. As we know, the bond energy of the ice is changing because the ice is turning from a solid, ice, into a liquid. So we write E bond. E just means energy, and the subscript bond tells us that the energy is bond energy. Now, what's happening to the bond energy? Well, it's actually increasing. We have to put energy into the ice in order for it to melt. So we draw a little arrow like this. Next, we need to write down how we know that this kind of energy is changing. We know that this kind of energy is changing because the ice is turning into a liquid. A way of writing this is that the amount of the substance, the mass of the substance, that is a liquid, is increasing. Originally, none of the ice is a liquid. It's all ice. And then, after a little while, it all turns into a liquid. Once the ice melts, we now have water at 0 degrees Celsius, the melting point of the ice. Now, this water is going to increase its temperature because it's surrounded by hot coffee. So, we write that the thermal energy, ETH, of the water is increasing. We know that the thermal energy of the water is increasing because the temperature, T, of the water is increasing. Lastly, let's think about the coffee. This is the simplest one. We know that the coffee is just going to get colder. This looks exactly like the melted ice case, except in reverse. The thermal energy of the coffee is going down because the temperature is going down. And there we have it, our first energy interaction diagram. Now, usually there's more stuff that we would draw here in the bubbles, but we'll save that for the next video. We don't need to worry too much about it now. We need to indicate whether this system is open or closed. We said that with the coffee and the ice in the thermos, this was a closed system. To represent that this is a closed system, we enclose the bubbles with an oval like this. If this was an open system, instead of drawing a solid line, we draw a dotted line. But we'll look at examples with open systems later. Now, what does it mean that the system is closed? What it means is that the total amount of energy inside the system is not allowed to change. Energy is being moved from one kind to another. Specifically, the energy in the coffee is being put into the ice, causing it to melt and warm up. Because the coffee is losing some of its energy, its temperature is going down. Now, at this point, we've made quite a bit of headway into describing our system very precisely. We now know very clearly which energy systems are changing and which direction they're going. This is probably more information than you had in your mental model of an ice cube melting in a warm liquid. But we're not quite there yet. We can't actually make a concrete prediction with this information. Specifically, we're going to want to know what the final temperature of the ice and coffee mixture will be at the end. To do that, we're going to have to introduce some math, and that's what we'll look at in the next video.